Fluid mechanics is the branch of physics that studies fluids and the forces on them. Fluid mechanics can be divided into fluid statics, the study of fluids at rest. Fluid kinematics, the study of fluids in motion. And fluid dynamics, the study of the effect of forces on fluid motion. It is a branch of continuum mechanics, a subject which models matter without using the information that it is made out of atoms, that is, it models matter from a macroscopic viewpoint rather than from a microscopic viewpoint. Fluid mechanics, especially fluid dynamics, is an active field of research with many unsolved or partly solved problems. Fluid mechanics can be mathematically complex, and can best be solved by numerical methods, typically using computers. A modern discipline, called computational fluid dynamics, is devoted to this approach to solving fluid mechanics problems. Particle image velocimetry, an experimental method for visualizing and analyzing fluid flow, also takes advantage of the highly visual nature of fluid flow. Brief history. The study of fluid mechanics goes back at least to the days of ancient Greece, when Archimedes investigated fluid statics and buoyancy and formulated his famous law known now as the Archimedes principle, which was published in his work on floating bodies, generally considered to be the first major work on fluid mechanics. Rapid advancement in fluid mechanics began with Leonardo da Vinci, Evangelista Torricelli, Isaac Newton and Blaise Pascal, and was continued by Daniel Bernoulli with the introduction of mathematical fluid dynamics in hydrodynamica. Inviscid flow was further analyzed by various mathematicians and viscous flow was explored by a multitude of engineers including Jean-Luc Copyright and Ard-Marie Poiseuille and Gotthelf Hagen. Further mathematical justification was provided by Claude Louis Navier and George Gabriel Stokes in the Naviero-Euro-Stokes equations, and boundary layers were investigated, while various scientists such as Osborne Reynolds, Andrei Kolmogorov, and Geoffrey Ingram Taylor advanced the understanding of fluid viscosity and turbulence. Relationship to continuum mechanics. Fluid mechanics is a subdiscipline of continuum mechanics, as illustrated in the following table. In a mechanical view, a fluid is a substance that does not support shear stress. That is why a fluid at rest has the shape of its containing vessel. A fluid at rest has no shear stress. Assumptions. Like any mathematical model of the real world, fluid mechanics makes some basic assumptions about the materials being studied. These assumptions are turned into equations that must be satisfied if the assumptions are to be held true. For example, consider a fluid in 3 dimensions. The assumption that mass is conserved means that for any fixed control volume enclosed by a control surface the rate of change of the mass contained is equal to the rate at which mass is passing from outside to inside through the surface, minus the rate at which mass is passing the other way, from inside to outside. This can be turned into an equation in integral form over the control volume. Fluid mechanics assumes that every fluid obeys the following: conservation of mass, conservation of energy, conservation of momentum, the continuum hypothesis, detailed below. Further, it is often useful to assume a fluid is incompressible that is, the density of the fluid does not change. Similarly, it can sometimes be assumed that the viscosity of the fluid is 0. Gases can often be assumed to be inviscid. If a fluid is viscous, and its flow contained in some way, then the flow at the boundary must have 0 velocity. For a viscous fluid, if the boundary is not porous, the shear forces between the fluid and the boundary results also in a 0 velocity for the fluid at the boundary. This is called the no-slip condition. For a porous medium otherwise, in the frontier of the containing vessel, the slip condition is not 0 velocity, and the fluid has a discontinuous velocity field between the free fluid and the fluid in the porous media. Continuum hypothesis. Fluids are composed of molecules that collide with one another and solid objects. The continuum assumption, however, considers fluids to be continuous. That is, properties such as density, pressure, temperature, and velocity are taken to be well defined at infinitely small points, defining a EV, at the geometric order of the distance between 2 adjacent molecules of fluid. Properties are assumed to vary continuously from one point to another, and are averaged values in the rev. The fact that the fluid is made up of discrete molecules is ignored. The continuum hypothesis is basically an approximation, in the same way planets are approximated by point particles when dealing with celestial mechanics, and therefore results in approximate solutions. Consequently, assumption of the continuum hypothesis can lead to results which are not of desired accuracy. That said, under the right circumstances, the continuum hypothesis produces extremely accurate results. Those problems for which the continuum hypothesis does not allow solutions of desired accuracy are solved using statistical mechanics. To determine whether or not to use conventional fluid dynamics or statistical mechanics, the Knudsen number is evaluated for the problem. The Knudsen number is defined as the ratio of the molecular mean free path length to a certain representative physical length scale. This length scale could be, for example, the radius of a body in a fluid. Problems with Knudsen numbers at or above 1 are best evaluated using statistical mechanics for reliable solutions. Navier-Stokes equations. The Navier-Stokes equations are the set of equations that describe the motion of fluid substances such as liquids and gases. These equations state that changes in momentum of fluid particles depend only on the external pressure and internal viscous forces acting on the fluid. Thus, the Navier-Stokes equations describe the balance of forces acting at any given region of the fluid. The Navier-Stokes equations are differential equations which describe the motion of a fluid. Such equations establish relations among the rates of change of the variables of interest. For example, the Navier-Stokes equations for an ideal fluid with zero viscosity states that acceleration is proportional to the derivative of internal pressure. This means that solutions of the Navier-Stokes equations for a given physical problem must be sought with the help of calculus. In practical terms, only the simplest cases can be solved exactly in this way. These cases generally involve non-turbulent, steady flow in which the Reynolds number is small. For more complex situations, involving turbulence, such as global weather systems, aerodynamics, hydrodynamics and many more, solutions of the Navier-Stokes equations can currently only be found with the help of computers. This is a field of sciences by its own called computational fluid dynamics. General form of the equation. The general form of the Navier-Stokes equations for the conservation of momentum is: where is the fluid density, is the substantive derivative, is the velocity vector, is the specific body force vector, and is a tensor that represents the surface forces applied on a fluid particle. Unless the fluid is made up of spinning degrees of freedom like vortices, is a symmetric tensor. Usually the stress tensor is decomposed as: where is a static isotropic stress state, and is the desphiatoric stress tensor, corresponding to the part of the stress due to the fluid motion. Generally, the scalar can be taken as the thermodynamic pressure, whereas is called the viscous stress tensor. Furthermore, the diagonal components of tensor are called normal stresses and the off-diagonal components are called shear stresses. The vectorial Navier-Stokes equation above can be written then as: this is actually a set of three equations, one per dimension. By themselves, these equations are not sufficient to produce a solution. However, adding other conservation laws and appropriate boundary conditions to the system of equations produces a solvable set of equations. The conservation of mass provides another equation relating the density and the fluid velocity. On the other hand, the identification of with the thermodynamic pressure is usually possible. Therefore, a thermodynamic equation of state must be used to connect the pressure with the density and another state property, such as temperature or enthalpy. This in turn brings another unknown to the problem so that an equation for conservation of thermal energy must also be solved along with momentum and mass conservations. In the case of an incompressible fluid there is no relationship between the pressure and the density. The Navier-Stokes equations and mass conservation are then sufficient to determine the solution to a fluid mechanics problem. Actually, the absolute pressure in an incompressible fluid is indeterminate, and only its gradient is relevant for the equations of motion. Taking the divergence of the Naviero-Stokes equation and using the mass conservation equation to simplify the result gives a Poisson equation for the pressure. Additionally, in order to close the system of equations, a constitutive equation relating the viscous stress tensor to the velocity field must be introduced. This constitutive model, which depends on the nature of the fluid, is the basis for the distinction between Newtonian and non-Newtonian fluids. Newtonian versus non-Newtonian fluids. A Newtonian fluid is defined to be a fluid whose shear stress is linearly proportional to the velocity gradient in the direction perpendicular to the plane of shear. This definition means regardless of the forces acting on a fluid, it continues to flow. For example, water is a Newtonian fluid, because it continues to display fluid properties no matter how much it is stirred or mixed. A slightly less rigorous definition is that the drag of a small object being moved slowly through the fluid is proportional to the force applied to the object. Important fluids, like water as well as most gases, behave to good approximation as a Newtonian fluid under normal conditions on Earth. By contrast, stirring a non-Newtonian fluid can leave a hole behind. This will gradually fill up over time. This behavior is seen in materials such as pudding, oobleck, or sand. Alternatively, stirring a non-Newtonian fluid can cause the viscosity to decrease, so the fluid appears thinner. There are many types of non-Newtonian fluids, as they are defined to be something that fails to obey a particular property. For example, most fluids with long molecular chains can react in a non-Newtonian manner. Equations for a Newtonian fluid. The constant of proportionality between the viscous stress tensor and the velocity gradient is known as the viscosity. A simple equation to describe incompressible Newtonian fluid behavior is: where is the shear stress exerted by the fluid, is the fluid viscosity a constant of proportionality, is the velocity gradient perpendicular to the direction of shear. For a Newtonian fluid, the viscosity, by definition, depends only on temperature and pressure, not on the forces acting upon it. If the fluid is incompressible, the equation governing the viscous stress is: where is the shear stress on the face of a fluid element in the direction, is the velocity in the direction, is the direction coordinate. If the fluid is not incompressible, the general form for the viscous stress in a Newtonian fluid is: where is the second viscosity coefficient? If a fluid does not obey this relation, it is termed a non-Newtonian fluid, of which there are several types. Non-Newtonian fluids can be either plastic, Bingham plastic, pseudoplastic, dilatant, thixotropic, heopectic, viscoelastic. In some applications, another rough broad division among fluids is made: ideal and non-ideal fluids. An ideal fluid is non-viscous and offers no resistance whatsoever to a shearing force. An ideal fluid really does not exist, but in some calculations, the assumption is justifiable. One example of this is the flow far from solid surfaces. In many cases, the viscous effects are concentrated near the solid boundaries, while in regions of the flow field far away from the boundaries the viscous effects can be neglected and the fluid there is treated as it were inviscid. When the viscosity is neglected, the term containing the viscous stress tensor in the Naviero-Stokes equation vanishes. The equation reduced in this form is called the Euler equation. See also: aerodynamics, applied mechanics, Bernoulli's principle, communicating vessels, secondary flow, different types of boundary conditions in fluid dynamics. Notes. References: Bachelor, George K., An Introduction to Fluid Dynamics, Cambridge University Press, ISBN A0-521-66396-2. Falkovich, Gregory, Fluid Mechanics, Cambridge University Press, ISBN A978-1-107-00575-4. Kundu, Piyush K. Cohen, Ira M., Fluid Mechanics, Academic Press, ISBN A978-0-12-373735-9. Curry, I.G., Fundamental Mechanics of Fluids, McGraw-Hill, Incorporated, ISBN A0-07-015000-1. Massey, B. Ward Smith, J., Mechanics of Fluids, Taylor and Francis, ISBN A978-0-415-36206-1. White, Frank M., Fluid Mechanics, McGraw-Hill, ISBN A0-07-240217-2. External links, Free Fluid Mechanics Books, Annual Review of Fluid Mechanics, Wiki The Computational Fluid Dynamics Reference Wiki. Educational Particle Image Velocimetry Resources and Demonstrations.